Let's do one more example of motion in the plane, and I want to motivate this by a very typical situation in basic physics, which is F equals ma, the force. If you know the force on some object, like a particle, and you know its mass, then you can figure out its acceleration. And so that's a very typical situation to be in. You know the acceleration of a particle. That's the second derivative of the position vector. And we want to get the position vector. So we can get parametric equations for the particle. We know x of t, we know y of t. We can sketch it. We can talk about its location at any given time. So that's going to involve integrating this twice. So this is, for me, the best motivation to start talking about why would you integrate a vector function as opposed to differentiating it. So, for example, to make it really explicit, suppose I know, maybe from something about the forces, but I know that the acceleration on a particle as a function of time is t, the x component of the acceleration is t, and the y component is 9 cosine 3t. So this combined is the acceleration vector as a function of time. And now I'm going to integrate that twice to get the position vector. Just like differentiating, that's just going to happen separately in each component. That's the beautiful thing about this story. But we know that every time you do an integration, you need to have some sort of initial condition to be able to solve for the arbitrary constant. So in this situation, I need to know where I start, that's r of 0, and what was my initial velocity, in what direction was I going and how fast, and then the acceleration, which is usually determined by the force, takes over. So this is a very important thing about physics, is you need to know the initial position and velocity of something, even if you know the force law. Without this knowledge of the present, you can't predict the future. So this is pretty easy. That's r double prime. So r prime or of t or v of t. I picked functions that are easy to integrate, so that's 1/2 t squared plus, let's say c1, comma, 9 cosine 3t, that's going to, the integral of that is 3 sine 3t plus c2. And then I have to figure out the c1 and c2. Well, I just plug in, we'll just put it in here since I have room there. That's v of 0, so I plug in 0 here. Luckily, this is 0 and this is 0, so that is exactly c1, c2. That's not in general, and we'll see an example in a second. But here, the t stuff actually went away, so I was actually staring at the c1, c2. So just to save space, you really should usually rewrite this, but just to save space, I'll put in the 1/12 here, and this happened to be 0, just because I'm trying to pick a fairly simple example. Okay, so there's my velocity. Already, that's interesting information. I know the direction and speed of this particle at any time, and sometimes I might actually just care about that alone and stop there. But if I know the initial position as well, I can integrate again and figure that out. Okay, so I'll do that. R of t now is 1/6 t cubed plus 1/12 t plus, I guess I'm up to c3, and then minus cosine 3t, antiderivative of this one, plus c4. And here, okay, I'm going to plug this in. So 0, minus 1. Again, this is 0, it equals 0. And so you just get c3. So c3 happens to be 0. And minus 1 is, cosine 3t when t is 0 is actually minus 1. So it happens to be, again, because I wanted things to work out pretty simply, that in fact c3 and c4 are both 0. But remember that in general, you're going to need to have those. They might not be 0. So there's our position function. Let's look at that and see if it fits with the information we already had. This is a moderately complicated one, so I'm going to use Desmos because that produces some pretty nice pictures. Okay, so there's our function, 1/6 t cubed plus t over 12 minus cosine 3t. And one nice thing we were just discovered literally today on Desmos is you can make a slider for the upper limit of the t limits, or probably the lower limit as well, of your function, and that allows you to animate tracing out the curve. So this, you can think of the head of the path here as the particle moving in time, and then it's just leaving a trace as it goes. So you can see that it's going relatively fast at the start, up and down, and then it slows down, especially the x motion slows down quite a bit and the y motion is fairly regular, and then it goes on its merry way. So does that fit with what what we saw? For example, the velocity information that was here, you can see that 1/2 t squared plus t 1 over 12, that's going to be just 1/12 when t is 0, much, much bigger when t is away from 0. The 3 sine 3t is just uniformly going up and down with magnitude 3, so that's not changing too much, although it oscillates in direction as we saw. Sometimes it's positive, so moving up, sometimes it's negative, moving down. But the 1/2 t squared plus t plus 1 over 12 is more fast than slow than fast. And of course, the r of t, one thing we can notice is that at the end of the day, this is between -1 and 1. That would have been not immediately obvious from here, and it is important that we had these conditions, that we got exactly just a minus cosine. And so that led to this behavior where the up and down motion was just between -1 and 1. Just to modify it slightly, suppose we had had just one little change in v of 0. Suppose that had been a 1. Oop, C2. Okay. Then this would have been 3 sine 3t plus 1. Seems like a fairly minor change. And kicking it with an initial upward velocity puts this as 3 sine 3t plus 1. Then that integral is going to add a plus t here. Let's see, does this still satisfy this initial position? Yes, when t equals 0, that's -1, so that matches. Okay, so just this little bit where I happen to notice it was going upward a little bit more than the other particle was, that's going to change the graph pretty significantly. If we go back to here, that adds a plus t here. And now I've added a progressively upward motion as it goes along. So it's wiggling, but it's also going up as it goes. And so that was a fairly significant change just because I changed one of the initial conditions for the velocity. And I think that's all I want to do with this example.